In this video, we're going to talk more about changing coordinates, and we're going to view the coordinate mapping as a transformation. We'll also look at how polynomials interact with the real space. Okay, so first, let's B be a basis for a vector space V. We say that coordinate mapping from x to x relative to B is a one-to-one linear transformation from V to R. So in the first part, we're going to cover the linear transformation part. And then later we'll do one-to-one. Okay, so linear transformation. There's two requirements for a linear transformation. The first one, we need to show that if we have vectors u plus vectors w relative to B, this is the same thing as the vector u relative to B plus the vector w relative to B. So again, this is kind of like saying t of u plus v is equal to tu plus tv, except we're just using different notation. So instead of this t, we're using these square brackets with the relative to a basis sign instead. So instead of putting a transformation capital T with brackets, we're using square brackets with the subscript b. So it's exactly the same thing here. Okay, so let's write out two vectors. So we're going to use these vectors for both parts of the proof. So u we're going to represent as c1, b1 all the way up to cn, bn, and w will be written as d1, b1 all the way up to dn, bn. Okay, so if we start with u plus w relative to b, well, again, we just take the coefficients from each. So this is the same as the vector c1 plus d1 all the way down to cn plus dn. But now that we're working with vectors, we know that we can split these numbers up if they're real numbers. So we can take c1 all the way up to cn, and then we can add the vector d1 all the way up to dn. And, just by definition, this is equal to the vector u relative to b plus the vector w relative to b. So that's the first step. The first step, we've shown that the transformation on adding two vectors is the same thing as the transformation on one plus the transformation on the other. Okay, the next step is for any scalar c times u relative to b. This just has to be equal to c times the vector u relative to b. So we're going to use our u, which is equal to c1, b1 all the way up to cn, bn from the last time, and we're going to do the same thing. So c times u relative to b, well, again, this is just the vector c. Oh, I shouldn't use c here. Let's use a different letter. Let's use r. Okay. ru, so this will be r times c1 all the way down to r times cn. We can factor out the r from each of these, so this is just r times the vector c1 all the way through cn, and this will just be equal to r times the vector u relative to b. So the two conditions here hold. Therefore, this is a linear transformation. So let's prove that it's one-to-one. Okay, so the one-to-one part. This is basically saying that if we have two vectors that have been transformed and they're equal to each other, then the vectors that haven't undergone that transformation will also be equal to each other. So we might have seen this before as stating that t times u equal to the transformation on b implies that u is equal to b. This is the same concept. So let's assume that u relative to b is equal to w relative to b. I'm going to use, again, the same u and w as previously so I don't have to rewrite it. Okay, so again, this is just c1 all the way down to cn, and we say that this is equivalent to d1 all the way down to dn. Okay, so at this point I'm going to left multiply both of these vectors by the transformation matrix. So I left multiplied u by the transformation, and I left multiplied w by the left transformation. So now what we get is we get c1b1 plus all the way up to cnbn, because again, this just gives us, so this is just multiplying the vector by the matrix. And on the right, we're going to get d1b1 plus ... all the way up to dnbn. At this point, on the left side, c1, b1, all the way up to cnbn, that's just the vector u. And d1b1 all the way up to dnbn, well, that's just the vector w. So we've proven that if we have u and w with respect to b, that's just going to give us u equal to w with respect to the standard basis. Okay, so we've proven that the coordinate mapping is a one-to-one linear transformation from V to Rn. Alright, so now with this, we can take polynomials in Pn to vectors in Rn plus 1. Okay, so why n plus 1? Okay, well, a basis for a polynomial is 1t, t squared, all the way up to tn. So we could write this as a0 plus a1t all the way up to an tn. So let's say we have p2. Okay, well, that's going to be a0 t to the 0 plus a1t plus a2t squared. So we can see here that there's actually going to be 3 elements in our basis, t0, t1, and t2. So if we have p to the n, we need n plus 1 spaces for entries in Rn. So the polynomial with respect to the basis is going to look like a0, a1, all the way up to an minus 1, and an. So we can see here that there's going to be n plus 1 entries. So what this means is that we can't take something like p2 and then have a one-to-one linear transformation to r2. That's not going to happen. It has to be to r3. Okay, so that's taking polynomials to the real space. So if we have a basis for p2 and we have a polynomial, then we can find the polynomial p relative to b. So we can write all of these vectors in the basis, these polynomials in the basis, into a matrix. So if we have 1 minus t squared, well, this is just equivalent to the vector 1, 0, negative 1, where we have, say, the t0s here, the t1s here, and the t2s there. Okay, so I'll do the next one. What about t minus t squared? Well, we have 0 t0s, we have 1t, and we have negative 1t squared. Okay, what about 2 minus 2t plus t squared? Well, this is going to be 2, negative 2, and 1. And then we'll also do our polynomial that we're looking at. So 3 plus t minus 6t squared. So this is going to be 3, 1, negative 6. So how do we solve this? Well, we just put it into a matrix and we row reduce. Okay, let's do that. So we're going to have our b1, which is 1, 0, negative 1, our b2, which is 0, 1, negative 1, b3, which is 2, negative 2, 1, and then our polynomial, which is 3, 1, negative 6. So now we could do some row reduction. Okay, so let's leave the first and second rows the same, and we're going to add the first row to the third row. So it'll be 0, negative 1, 3, and negative 3. Okay, then what we'll do is we'll take the second row, or we'll take the third row and we'll add the second row. So we'll leave the first one the same. 1, 0, 2, 3, 0, 1, negative 2, 1. And we'll add the second row, so 0, 0, 1, 1 and negative 2. Okay, so now what we get is we get that our t squared here, so I'll just call these C1, C2, and C3 just like we had before for vectors relative to b. So our C3 is going to equal negative 2. Okay, so our second equation says that C2 minus 2C3 is equal to 1. So C2 plus 4 is equal to 1. So our C2 is going to be negative 3. And then our first row says that C1 plus 2C3 is equal to 3. So C1 minus 4 is equal to 3. So C1 is equal to 7. So therefore our polynomial, respect to b, is going to be the vector 7, negative 2, negative 3. Okay, so that's how we do it with polynomials. It's pretty much the same as we did it in the real numbers. Okay, or I should say the real space. Okay. So, here's a quick diagram of coordinate mapping. So I have a vector space V, and in this example I have R3, but this really could be Rn, anything in Rn. So we have a vector in our space V. So what we do is we map it to some point relative to B by taking the transformation on it. And this transformation, you could write this as brackets with a B, you could write it as a transformation T, so this could be T of X, but as standard notation, the brackets with the B, we know it's relative to a basis. So this is what we do. We take a point in some vector space. It doesn't even matter what vector space it is. It could be, this could also be Rn, if we want it. This could be Pn minus 1. So it's a vector space, and whatever we have there, we can just map in the real plane, real space, 3D reals, whatever. Okay, so that's it for the change of coordinates matrix. If you have any questions, please leave them in the comments below, and I'll answer them the best that I can.